Hey, Algebra 2. Today we're going to continue 4.4, more log stuff, okay? And our goals today is to go over how to do an inverse for a log, how to cancel out logs, and talk about two special types of logs. So let's go a little backwards, I guess, from how I just said it, and let's get rid of how to get two special type of logs. All right. First off, we just have log with no number on the bottom. If you do not see a number, so the number is completely blank or doesn't exist, for example, log of 2, but there's no base number, okay? Or log of, let's make this 100. There's no base number here. If you do not see a base number here, the number you're going to assume is 10. And let me explain a little bit why 10. Let's think about how this or what these means. Let's do the top one actually. This one is not that good. Let's do the top one. So log, if you didn't see it, 100 equals x. So we know if you don't see it, it's a 10. So in order to remove the log, you move it and it slides over to become the base of the exponent. So it's 10 to the x power. Then you think, what x power gets me 100? Well, x would equal 2 in that case, because 10 times 10 would give you 100. Now, usually we say log, usually when you don't see a number, it's like 1. But what's my problem with 1? Let's do the same example. What's my problem with 1? I'll make it y. Well, let me slip the 1 here. 100 equals 1 to the y power. Wait a second, there's my issue. No matter what exponent I put in for 1, it will always be 1. 1 to the second power is 1. 1 to the third power is 1. 1 to the billion power is 1. So that's why log, when you don't see it, is not 1, but Greeks. So people, let's see, that's probably what, 1700 years ago? Actually, no, this is Algebra 2, so this is 900 years ago. This right here was decided that they're going to use 10, okay? And not 1, because 1 wouldn't make sense. Now, I told you a lot of things, but the moral lesson is this. If you just see a log, let's say it was 6, and there's no number here, the number is 10. If you don't see a number, it's automatically 10, okay? Now we have another type of log. It's called ln. This is called a natural log. So ln is the same thing as log base of e. That E should feel familiar. That E is something we did with graphing growth and decay, and I think it was in section 3.6. It was in the last chapter. Or maybe not. Maybe it was 4.1, actually. Let me check a second. Oh, no, it was section 4.3, just a section ago. E was the base. That's natural log. Again, I told you from before and I tell you now, you don't really need to know what's so special about E. Just know that if you see a ln, that's the same thing as log base E. Okay, so there's some special things. Now, let's go to inverses. Now, what is an inverse? Now, if you don't remember how to do an inverse, let's do a generic one. Let's say y equals 2x plus 5. I want to find the inverse. Does anyone remember what's the first step of finding the inverse? It is swapping the x and y. So x equals 2y plus 5. Then you get the y by itself. So I would subtract 5 on both sides. So x minus 5 equals 2y. Then divided by 2 on both sides. So x minus 5, all of that divided by 2 would equal y. And that would get me my inverse. So that's how we found inverses in what we call a linear equation. So just a normal equation. Now we're going to find inverses with logs, which, trust me, is not that bad. And before we actually do find inverses, let's talk about what we call the inverse properties. So if you remember, let's say it was like 3 squared equals 9. If I square root both sides, that cancel out, and I square root here. So it becomes 3 equals the square root 9. Both things are true. So you could cancel out something like that by using the opposite operation. So with logs, you could kind of do the same thing. So I'm going to make one up. Let's see. Let me think of one. Oh, I got one. So let's say 4 to the exponent log base 4. Let's make this 10. It doesn't matter what number it is. Okay. So it's 4 exponent to the power of log base 4 10. Here's something really important. If the base of the log and the base of the exponent matches, you could cross both out and make this number here a normal number. So since this is base 4 and this is base 4, base of an exponent and base of a log, this just becomes 10. So your answer here when you simplify is 10. Let's try another one. 6 log base 6, 15. Well, wait a second. These are the same base. So once again, I could cross them out. All that's left is 15. One more time. 7 log 7 x plus 3. 7 and log 7 is the same base, so you cross that out. So then this is just x plus 3. And let's say it would equal 10, let's say. So it equals 10 minus 3 minus 3, x equals 7. The fact that this is 7 and that's 7 is coincidence. Don't think they'll always match. But see, if you have the base of the log and the base of the exponent matching, you could cancel them out. So it also works in reverse. So what do I mean by reverse? Log base 4, a normal size 4 to the 10th power. Last time it was 4 base of an exponent to the power of base to the log. Now this is base of a log to the base of an exponent. They still cancel out, and all that's left over is 10. Let's do another one. Log base 6, 6, 15. Log of the base of the log and base of the exponent matches. You could cross that out. All you're left with is 15. One more time. Log base 8. Let's go 8x plus 2 equals 11. Well, log base 8 and 8 matches completely. So x plus 2 equals 11. Minus 2 minus 2. X equals 9. So if you have the same base for both the exponent and the log, you could cancel them out. Just like here, or just like here. So finally, we're going to do what we said in the beginning and find the inverse. I'm going to type up the steps in the Google Classroom post so you could follow up there, so I don't have to spend whiteboard space here. So step 1, you're going to swap the x and the y position exactly as they are. So y is a normal size y. When you swap it, x is a normal size x. 6, this is an exponent. So instead of being 6 to the x power, it becomes 6 to the y power. So the first thing you do is swap x and y. Whenever you hear the word inverse, big hint, you're going to swap x and y. When it says find the inverse, I should say. Okay. Now, I want to get rid of this base of an exponent. What have we been learning this whole time about base of the exponents? What's the opposite of base of the exponent? It is the base of the log. So if I start off with an exponent, I should end up with a log. So over here is going to be log base 6 x equals y. Log base 6. Why is it base 6? Because this number was base 6. So log base 6 x equals y. So I take the bottom of the 6 and make it the bottom of the log. The bottom of the exponent becomes the bottom of the log. Let's do another one. All right, magically this one appeared. Y equals log 3 plus x. Wait a second. Mr. Tobel, there's no number on the bottom. In the beginning of the video, I said there's a number that belongs to the bottom of the log if you don't see it. And since I don't see it, I'm going to plug in that number, which is 10. So it is technically log base 10, 3 plus x equals y. Step 1, swap the x and y for wherever they are. So x becomes the y. And y becomes the x and x becomes a y. So then this is y now. All right, now our goal is to get y by itself. The only thing left here is the log base 10. Everything's in parentheses here. So log base 10 is on the outside. So I have to move it over here. Over here, the base of an exponent becomes the base of a log. So what is the reverse? The base of a log becomes the base of an exponent. So this is 10 to the x power equals 3 plus y. 10 to the x power equals 3 plus y. I'm going to subtract 3 on both sides. So then I have 10x minus 3 equals y. Y is now by itself, so I am done. I'm going to do about 2 or 3 more. Again, magically appears the new problem. 2 times ln x plus 3 equals y. ln, what is ln? ln is called natural log, and I said in the beginning of the video, you could rewrite this as log base e. So the letter e, x plus 3 equals y. So step 1, we're going to swap the x and the y. So 2 log base e, y now, plus 3 equals x. Now, in the second step, it said to get the log or exponent by itself. Now, this is where it actually matters. In this step over here, it was already by itself, so we were happy. So here, we're going to divide by 2 first, and I'm going to divide by 2 here. So now I have log e, y plus 3 equal x divided by 2. Why did I divide? Because I'm multiplying 2 in log, so the opposite of multiplication is division. Okay, so I have a log base e, so the base of a log when transferred over becomes the base of an exponent. So now I have y plus 3 equals e. This whole thing becomes a fraction, so x divided by 2. E to the power of x divided by 2. All right, last step, subtract 3, subtract 3. Y ends up equaling e to the x divided by 2 power minus 3. Okay. One more sample, and this will go under simplification. Let's do number 32 from the homework. So log base 6, 36x. So log base 6, 36 to the x power. Okay. So how the heck do I simplify this? 6 and 36 are not the same number. 6 and 36 is not the same number. So 6 and 36 is not the same number. This is a big issue. Because all I know is how to simplify when I have the same exact number. Well, let's see. I know 6 and 36 has a special relationship. 6 squared equals 36. How can I use that to my advantage? Well, I know 36 equals 6 squared. So what I'm going to do is rewrite 36, so log base 6. I'm going to rewrite that 36 as 6 to the second power. That x was here, so we got to redraw that x, okay? So please pay attention what just happened here. You, as a smart Algebra 2 student, you look at this and you say, 6 and 36, I know there's something relationship between 6 and 36. Well, I know 6 to the second power is 36. Maybe you say to yourself 6 times 6 equals 36. Well, 6 to the second power equals 36. And I want this to look like 6. So I want to make this 6 look like, I want to make this 36 and match the 6. So I substitute 36, which is here, with 6 over 2. 6 over 2. So 6 over 2 here. And then you have your little exponent of x. But we don't really need to draw through parentheses because there's not much happening. So it just becomes 6 to the 2x. Now, how does that help? Well, that helps because since this is the same and this is the same, crisscross, get out of here. All is left is what my exponent was, which is 2x. So my answer for this question would be 2x. Let's do another one. Let's do 33. They even circle it so they know it's a good question. So 33 log base 3 81 to the x power. Dang, if it matched, I could cross this out. It'd be easy. So I gotta see, is there a relationship between 3 and 81? Is there a relationship between 3 and 81? Well, 3 squared, 3 times 3 is 9. So 3 squared equals 9. No, that doesn't work. 3 times 3 times 3, so 9 times 3 is 27. Nah, that doesn't work. 3 to the 4th power is 81, because 3 times 3 times 3, which is 27, times another 3 is 81. Hey, wait a second. That's a special relationship they have between each other. So 3 to the 4th power equals 81. If 3 to the 4th power equals 81, I can replace this 81 with 3 to the 4th power. So I'm going to rewrite this as log 3 to the 4, and don't forget Mr. X over here. Hey, now since the base of the log and the base of the exponent match, I could cross them out, good riddance, and all I'm left with is 4x. So all I'm left with here is 4x. And that's really good. We're really happy with just 4x. So I hope this helps you out with the homework. I know this stuff is difficult, so I'm going to have a Zoom session. You come in and ask your questions, okay? Otherwise, have a wonderful day.